Hi guys. Hi guys. This is Dr. Manjunath Chennapagod from Anveshana Academy, Bangalore, India. So in the previous video, we were discussing about numericals on Carnot engine or Carnot cycle. So now I will move towards next numerical on Carnot cycle or Carnot engine. So numerical on Carnot engine or Carnot cycle. So today I am going to do fifth numerical on Carnot engine or Carnot cycle. So I will read the problem first. A cycle heat engine operates between a source temperature of 1000 degrees Celsius and a sink temperature of 40 degrees Celsius. So there are two reservoirs. One is a hot reservoir, another one is a cold reservoir. They both are working at 100 degrees Celsius and 40 degrees Celsius respectively. Fine. Okay. What actually is asking find the least rate of heat rejection per kilowatt net output of the engine. That means what actually is telling the students, there is a heat source or hot zone, and one more is a freezer or a cold zone or cold sink. Hot zone works at a temperature T1. Cold sink, it works at a temperature T2. The T1 he has given, that is how much, 1000 degrees Celsius he has given. That you can convert it into Kelvin by adding 273. Hence it becomes what? T1 is equal to 1273 Kelvin. Okay. Then heat is going to reject through the sink. That also he has given, that is T2 is equal to 40 degrees Celsius he has given. That you can convert it into Kelvin by adding 273. So that is equal to what? T2 is equal to 313 Kelvin. Okay. So because of these two temperature difference, the engine is going to do some amount of work. That work is represented as a capital W. That can be calculated with the help of an equation, that is the capital W is equal to Q1 minus Q2. Okay, that too here what actually is telling now, per kilowatt. That means what amount of work done by the engine is 1 kilowatt. He has given per kilowatt how much amount of heat is getting rejected, that you need to calculate. Okay, how to calculate that we will do step by step now. So first you have listed out what is the inlet temperature, sorry, source temperature. That is a hot zone or hot reservoir temperature is 1000 degrees Celsius. Cold reservoir or cold sink or a sink temperature is 40 degrees Celsius. The net power output, the work done by the engine is 1 kilowatt. These are the data he has given. So for this we need to calculate the amount of heat rejected. So for that what we have to do, we have to follow some procedures here. What are the procedure? First one, identify the temperatures. T1 and T2 have to identify, and you have to list out. Then try to calculate the Carnot efficiency, because to calculate the heat rejection from the engine can be calculated with the help of a Carnot efficiency. So therefore you need to write the Carnot efficiency formula, that is what TL divided by TH actually. So that we need to write it down, dear students. Once you calculate the Carnot efficiency, then we can easily determine the work done, because we know Carnot efficiency is nothing but what? Work done divided by heat supplied. If once you know the Carnot efficiency and heat supplied, you can calculate the work done. That also you can calculate work done. Once you know the value of work done, so you can calculate the QS also. How to calculate that also I will tell. Once you know all the heat supplied and heat rejection efficiency, once you know all the things work done, you can calculate the heat rejection. How it is, that we know already. W is equal to what? Q1 minus Q2. We know already W is equal to Q1 minus Q2. If once you know the value of W, once you know the value of Q1, then you can easily calculate the Q2. So we can calculate the heat rejecting from the engine can be calculated with the help of equations. So that we can, that calculate heat rejected can be expressed in terms of what? Per kilowatt we can express. This is the procedure we need to follow to solve this numerical. For that, what you have to do then? First step, convert the temperature. So wherever it is there at 1000 degrees Celsius is the rate and 40 degrees Celsius is the rate. Convert it into Kelvin. The same thing I kept it here now. I have shown in the diagram. Fine. Next. So what you have to do then? So first what to do? You have to do the calculate the Carnot efficiency. What is it Carnot efficiency? 1 minus, you can express TL divided by TH. TL divided by TH, or efficiency is equal to 1 divided by heat rejected divided by heat supplied. With the help of these equations you have to calculate. Then with the help of Carnot efficiency, what I can do, I can calculate the heat input. That means what? Heat supplied, that QS you can calculate. That's the one thing. Once you know the value of QS and heat efficiency, you can calculate the work done. With the help of that work done, what you can do, you can calculate the efficiency. Already you know, right? Efficiency is equal to W divided by heat supply. With the help of Carnot efficiency and heat supplied, I can calculate the W. Once I know the value of W, what I can do now? I can calculate the heat rejection. That is nothing but Q2. So Q1 minus Q2. I can calculate the value of what? Q2 is equal to W minus Q1 minus W. So with help of this Q1 and Q2, I can calculate the value of what? Q2, heat rejected. So heat rejection I can calculate. So heat rejection I can calculate here now. One thing. And also once you calculate the heat rejection, what you can do, you can easily express that heat rejection in terms of kilowatt hour. So that is what? Carnot engine heat rejection per kilowatt hour power. Okay, so now you can see this is the what history of the numerical what he has given. Fine. So now what I have to do then? As I told, we need to calculate the Carnot efficiency. That Carnot efficiency is equal to 1 minus TC divided by TH. Okay, what is TC? We know already 313 and TH is 1273. With the help of this data, what I can do, I can calculate the Carnot efficiency. So Carnot efficiency is how much? After calculating the Carnot efficiency, we are going to get here the final efficiency is 75.41%. This is the Carnot efficiency. With the help of this Carnot efficiency, we can calculate the relative efficiency. We can relate this efficiency and we can calculate work done and heat rejection. How it is that we can see, dear students. We know efficiency is equal to W divided by heat supplied or heat added. Okay, or high temperature, heat of high temperature region. So that is nothing but eta is equal to W divided by QH. With the help of this, we can calculate the QH. QH how we can calculate? So QH is equal to W divided by neta. Okay, QH is equal to W divided by neta. So therefore QH is equal to, what is W? 1 kilowatt. What is neta? That is 0.754. Then how much you will get? You will get heat added or heat supplied is equal to 1.32 kilowatt. 1.32 kilowatt. Once you know the heat supplied, then heat added, then you can calculate heat rejection. How it is now? That is W is equal to QH minus QC. We know already that W is equal to Q1 minus Q2, where Q1 is nothing but what? Heat supplied, that is QH here now. Some authors they will take Q1, some authors they will take QS, some authors they will take QH and QC. Okay, cold reservoir and hot reservoir. Okay, so now hot reservoir minus cold reservoir. So this is the equation. Now what actually I want heat rejected from the heat rejected to the cold reservoir or cold sink. That is nothing but QC is equal to QH minus W. So therefore what QC is equal to QH minus QH minus W, right? What is QH? QH is equal to 1.32. That we already calculated here, 1.326 minus what is the W? W equal to how much? What is the value of W? W already you know. What is that? 1 kilowatt. Why it is 1 kilowatt? Because in the problem itself P has given 1 kilowatt. Then substitute here, you are going to get heat rejected in the sink is 0.326 kilowatt. Once you've done this, you can calculate the work done per kilowatt. That is nothing but what? So we need work done per kilowatt. That is heat rejected per kilowatt. How to calculate that now? Heat rejected divided by work done. So heat rejected is equal to how much? 0.3 kilowatt divided by 1 kilowatt. That means what? QC divided by QW is equal to 0.326 kilowatt per 3.26 kilowatt per kilowatt. That is the what heat rejected from the engine to the sink. So therefore the least heat of the rejection per kilowatt net output is the 0.326 kilowatt. This is the final answer, dear students. Thank you. Dear students, please subscribe my channel. Do like and comment and share and support me. Thank you.